Welcome to the, good morning, welcome to the Warren Lecture Series. Today's lecture would be given by Professor Tomasz Hueckel. Tomasz is known to many of you because he has been in the department for various occasions. He's a very good friend of the department. He got his, received his master's degree in civil engineering from Poland, from University of Technology in Gdańsk. And also in Poland, he got his PhD, but at the Polish Academy of Sciences in Warsaw. And eventually he went to France, where he did so-called habilitation, or Doctor of Science degree, in University of Grenoble. Then Professor Hueckel taught in many international organizations in Italy, institutions in Italy, which brought him knowledge of Italian and French, as you know. And eventually he came to Duke in 1987. His research interests are in theoretical soil mechanics, rock mechanics, and environmental geomechanics, and also in theory of plasticity. He is a co-founder and editor-in-chief of a new journal, I believe, which was started in 2015. He will advertise it. He is also on editorial board of various, is a member of editorial board of the various journals such as Numerical Analytical Method in Geomechanics, Archives of Applied Mechanics, International Journal of Mechanics of Cohesive and Frictional Materials, and many more. It's enough. I got a sign that it's enough. And I give an insider information that Professor Hueckel is an aspiring author, artist. I'm not sure if he will show us a piece of his art. He does a wonderful cut-off art. And with that, I will not take any more time. Please join me in welcoming our old friend.
Thank you, Sonia. It's a great pleasure indeed to be here. I don't even remember which is this, what is the number of the occasion. I must say that Professor Verhest offered me a postdoc here 30 years ago, and I'm afraid, I'm sorry, but I went for this easy solution of tenure track position at Duke. But you cannot walk back your life. Anyway, so I would like to start with this shameless advertising. These days, I think it's everything goes. So you are most welcome to submit a paper to this journal that, in addition of being obviously related to energy and environmental geomechanical issues, it's open to any fundamental papers in broadly understood area of geomechanics in general. So if you have something on capillary forces or any area that is a good excuse to put that to the journal, we are looking all the time for good papers. So send them in. Okay, today I will be talking about resilience in geomechanics, and the explanation for it is that this is about assessment on physico-chemical degradation of geomaterials. And as you see, this is a combination of two subjects that I have been working for some time, for a number of years, which are both degradation because of the chemical reactions in geomaterials that goes at the same time as loading activity, and the effects of capillary pressure, which is perhaps a more narrow subject. Anyway, before I go anywhere further, oh, I lost one slide. What happened? Yeah. So first, being you mainly young audience, I think you'll be required to put through a dictionary of difficult words. which are essentially words that are invented by our academic administrators to get money. And so these are new words for all subjects. And one of them is degradation, which I define in technical terms as a process of gradual loss of engineering qualities of material structures or systems over time. And that happens obviously, and this will almost to any material structure or system. More narrowly, I will be dealing with the mineral dissolution and drying of geomaterials. The next difficult word is the resilience engineering. This is the newest one. You will recognize that this is a cousin of a subject that has been brought to our community maybe 3 or 5 years ago. Sustainability was the name. I think sustainability already disappeared from most of dictionaries, but we have instead resilience. Resilience was brought, I think, mainly, well, it's a objective, one of the objectives of design to ensure the ability to absorb damage induced by combined long-term exposure and short-term exposure following that to extreme adverse events, and without suffering complete failure, and with an intrinsic capability to restore at least some of the critical functions. So it is a dream. I am sure that in some selected occasion it is feasible, but well, let's dream together. This is done mainly, the resilience engineering at this point, I think, is done mainly through something that is called PA, which is performance assessment. And performance, this is the last difficult word that I have compiled for you, and here it is. This assessment, which is a process, provides a proof of satisfactory response to a number of absolutely thought out scenarios. We include chain scenarios of local failures of a system over the entire service life of the system or structure or material. And it is done mainly through mathematical modeling. And for examples, our environmental impact statement that for almost any new project in most states, I don't know about what will happen from now on, but until a year ago, it was required in most places. It is required by National Research Council for Nuclear Waste Disposal Program, so you have to provide such a performance assessment. So what is it? It's essentially checking the possible behavior of systems, not in the routine type of loading, but at any possible, or impact of a missile or earthquake in where there's no earthquakes. Florida, perhaps. Minneapolis. So the effect of earthquake in Minneapolis, you know, et cetera, et cetera. So because they may happen, right? So we are supposed to provide that performance assessment. So that refers, now, so where I was before I went there. Okay, let's continue. So this resilience engineering derives from the not necessarily successful performance of certain structures during recent events like Hurricanes Katrina and Sandy, repeated flooding across US and European Union, including coastal flooding that might be a result of the effect of rising ocean level, the tsunami disaster in Fukushima, the overall deterioration of the roads and bridges. I sound a little bit like a recent candidate for presidency, I think, including all these negative things. Inundation of the cities, and et cetera, et cetera. So what happens is that we would like to avoid all these things. And that is expected to become practice for complex and large infrastructure systems. Certainly nuclear waste disposals, since I have been in this business for almost 30 years, it was always there. CO2 sequestration facilities, they should go through that. That means that they should perform over the years that you can specify, well, in terms of nuclear waste disposal, 200,000 years, right? But other structures, probably the timing would be more modest. But all these new unconventional energy facilities, Earth security system like levees, should be checked against the combination of long-term exposure and extreme events. And they should stand out there and should be recoverable, right? What else we would want? Okay, let's see. So let's go back to this friend of mine. So you know this guy probably from many occasions, but one of them is related to the very structural design thing. So this is his confession. As you know, he has been called a number of times to confess in front of the Holy Inquisition. Apparently one time for confessing Copernicus' theory too loud. And, but the other occasion, which is less known, is about the theory of cantilever. As you know, in 1638, he published this with this figure, in which he gave the formula for the displacement of the tip, right? So the Inquisition asked him about the deflection of the beam in 2010. I think the first time I used that was in 2010, so you can, I should correct it, I forgot. It's 2017. All right, so, and his answer was very conservative, the usual one that he invented in 1638, but that was the Holy Inquisition response to his answer, and he said, that is the problem. The problem is it's degradation. It's one of the subjects of our presentation, and as you know, Galileo ended up behind bars for many years, and people say because of Copernicus, but we know very well that this is the reason. He simply ignored the degradation of structures. And we are not ignoring it, but we try to go ahead. So now we have to run through all these things that I already have shown you. So what's the today's classical design? Well, we will design structures like this. We will use the Young's modulus, for instance, in this case, of the structure as it is coming to the building site, a fresh, completely new material, right? And the moment of inertia of the structure that has not been exposed to any loss of the area, which is not true. That's the wood after 40 years, right? And many other structures. As you know, most of the structures, except few, would fail after 40 years or 60 years or 80 years. Rarely they will fail immediately after construction. Some of them do, right? But we will not talk about those, right? So there is an intrinsic inconsistent in our approach to design. So that's a grave accusation. So I will try to sweeten it up. So this is one of the examples from your home. I was sort of reluctant to go too far because I'm sure that you know much more details. In one of the claims of the Transportation Safety Board office, they were claiming that the fracture of the gussets because of the, as you can see clearly, advanced corrosion contributed to the failure of the bridge. But, I would gladly hear other opinions about that. And many other bridges have been neglected. But you cannot say that we never thought about that. We do think about that through this invention of safety factors. We simply say, well, we don't consider the yielding stress, for instance, in calculating the limit moment in the beam, but we simply divide everything, the allowable stress, from bearing capacity of ultimate stress by the factor of safety. And this concept has been with us for almost, 300 years or 400 years, right? From Coulomb and Bellidora, et cetera, et cetera. So we cannot say that we simply ignore the fact that there is an effect on structures. But, well, everything that is older than 300 years, I think deserves a second look. Here are just listed what are the commonly used factors of safety. And you notice the first thing is that all these are round numbers. Any round number in engineering, young colleagues, are suspicious, right? You know that very well. Okay, so how we calculate them? We estimate accuracy of load. We estimate the actual strengths. The wear estimates and environmental wear are included somehow. And the consequences of engineering failure, meaning money to pay for a broken dam or the cost of over-engineering of a component to achieve the required factor of safety. So I have been looking into a little bit about what happens with the factors of safety, and I found this wonderful theory about Eurocode of 20 years ago, and this is a characteristic value of the resistance. And this is a generic formula. The pluses do not mean pluses, but they imply to be combined with. Sorry. I'm sorry. They must be selling me an insurance. Let me do this. So anyway, I think they might have been from the Office of Factors of Safety, maybe. Because I will try to tell you that this is not a thing that I would like to participate in evaluating factors of safety. What I propose instead is this. We have tools to evaluate long-term effects of environment. We have tools to evaluate long-term effects of possible unpredictable, in theory, types of loads, right? Temperature or chemistry or anything else. We just need to sit down and do it. There are tools at your disposal. We just have to develop them to the engineering level. The long-term behavior is being studied currently, for instance, for geological barriers in nuclear waste disposal. And the performance of 100 years or 100 or 20,000 years from now is considered in such things. And I may add that, for instance, in 1945, there was since this was before I was born by 3 months, I didn't know about that in 45, a bomber on a routine flight hit an Empire State Building. And since then, the performance assessment was required for about 7 years on high rises. And after that, they said, for 7 years, nothing happened of that sort. Let's forget about that, right? Until, obviously, the World Trade Center tragedy. So what we will be talking about mainly is mathematical modeling of various scenarios in various instances, and they are most commonly multi-physics and multi-scale scenarios. And you will see what that means. Oh, these are the photos of this Empire State Building bombing, right? So, as I said, the community reacted to it very positively. People started looking at accidental loads, unpredictable loads on number of structures. But the practice has been very soon abandoned, probably because they required additional costs, as usual. So, in nuclear waste disposal, performance assessment is a common thing. We discussed, for instance, possibilities of either stochastically sort of induced type of cracking between the two boreholes or two tunnels in which the nuclear waste is disposed, and deterioration, both from the mechanical point of view and hydraulic, as you can see, and possible leakage of the contaminant, etc., etc. So these things are done and are doable for many structures. Okay, so let's talk about the degradation first. And what we will be doing, we will be trying to understand how a loss of certain properties of material, and that includes strength and stiffness and permeability, can be induced through environmental processes of the surroundings of a given structure. And these processes can be hydric, chemical, biological, thermal. Usually, most of them are being treated today as non-mechanical. The emphasis of my talk is about the coupling between those processes and mechanical processes. And these processes, just to give you a sense, they include addition, loss or loss of mass via chemical reactions, via erosion. They are certainly enhanced by mechanical conditions of stress or damage, and they are often coupled with transport of species that produce some of those processes, like advection or diffusion or reactions. What is the opposite to degradation, to be in the spirit of dictionaries? The antonym of it is material improvement. So it is the same thing that you would do, right? You have to improve to contrast those changes. So the question is, practically, that we want to answer is, how long a given structure will last? You know, this concept in engineering never existed. We don't really know how your house was supposed to last. Has ever anybody answered your question in this sense? A building here and there? They usually go out because they are not nice anymore, so we destroy them before they really technically go depleted. So my proposal here is to repeal and replace the concept of creep that is being currently used with to determine the long-term behavior. But what we know what we want to replace it with. It's with driving mechanism that we know. Well, the drawback is that we are not very well prepared to repeal and replace, because our understanding of degradation paradigm is not yet complete. And our degradation theory is not yet very good. And I want to distinguish one paper of my friends, Antonio Hens and Roberto Nova, 1993, when they talk about damage of bonded materials through chemical reactions. Okay. Other non-mechanical driving processes are listed here, and you can just have a very quick glance. One of them is acid rain, that is considered in very many cases to be a secret reason why slopes fail, right? And asphalt moisture damage is a very popular thing in the pavement industry. Desiccation cracking applies to almost everything, right? So there are other areas of engineering except for geomechanics, and I'm running through this photo very quickly because I think that Sonia will start getting nervous soon. All right. So what is the degradation paradigm? The paradigm essentially is centered around the coupling between an elastoplasticity theory for description of materials until failure with addition of an environmental hardening parameters. So we will essentially add to plasticity additional parameters that are coupled with fields of temperature, moisture, dissolution of minerals, ion change, and in general mass removal that could be, for instance, through erosion, right? That may happen along the process of loading. The most interesting particular feature of this paradigm is necessity of operating at different scales, because we know that the concept of multi-scale is artificial. We simply know that we know something about some of these processes, but on micro scale. For instance, the whole chemistry is on the molecular scale, right? So all analytical or quantifiable chemistry is on molecular scale. So we have to upscale that to our level of reasoning. Okay, so this is main tool. That's the chemistry, the plasticity in chemistry shop, right? So this lady is doing a plastic limit test in this very moment. The chemical corrosion of rocks is a very common process. You can see this at any excursion you take to the national parks. Or you go to the lab, and this experiment has been performed on a calcarenite, which is a very soft rock, but quite popular in many places, including southern Italy, which is a carbonate rock. And this one has been exposed simply to short periods of time, of the order of a few days to at most a week, to different levels. So this one was performed in usual manner in a quick exposure to laboratory condition. This has been exposed, I think, to water for about a week. So you see the change in the stiffness, you change in the peak stress. That one, the brown one, was exposed to, I think this one, these two, were exposed to water with some addition of acid. Acid, oftentimes, it's a natural acid from decomposition of of grass or wood at the top of the mountain that increases, acidifies pore water, which flows under the roots and oftentimes reaches the areas of ancient slips and can trigger a landslide, for instance. Anyway, so here are other beautiful photos of erosion. And now I am coming to the principal phenomenological postulate. So in order to deal with the effect of changing chemical environment on materials, we propose something that we will call chemoplasticity. And the first thing to say is that suppose a material is dissolved at a constant stress sigma, like in this picture. This is the initial yield limit in QP prime space, right? And if we allow certain exposure, the chemical softening will occur what that means. That means that the yield surface is becoming much smaller. It is becoming much smaller until it will happen that the yield surface fulfills the equation of yielding at this given constant stress. So essentially it shrunk until it touched the yield, the stress point. And what that initiates is the stress which is nominally elastic, because it is within the original initial yield surface, that it starts producing elastoplastic strain, or in particular, in this case, a plastic strain. Well, this plastic strain, in addition or in analogy to thermoplasticity, will start to produce also a component of strain that depends on chemical process, right? On the chemical process of dissolution, in analogy to the term in thermoplasticity, where you have a term that is dependent on temperature. Very simple, nothing complicated. Anyway, so here it is, the formula for the yield surface at dissolution, for instance, at constant material. There are others, so these are usual stuff. This is the usual mechanical stress invariants. This is the plastic strain, accumulated plastic strain that corresponds to hardening. These two are the chemical tricks. So this is an integrated from zero of the time count until the current moment of mass lost of minerals, 1, 2, 3, 4, 5, or just one that you believe is really important to make things simpler, right? And that's the time of integration. And this one is, so this is the mass of the solids that are being removed from the solid part of the skeleton through chemical reaction. This, instead, is concentration of for instance, an ion in pore water. Clays, for instance, would react mainly to this. And the row of them is trickier because this changes much in time. It accumulates in time. This is instantaneous. So there are two different types of possible mechanisms. So for instance, if you reduce the population of calcium ions in water and replace them with sodium, there will be a very strong effect in terms of swelling of clays, right? Which, as you know, swollen clays are much weaker. They are less permeable, right? So they have dramatically different mechanical properties. So why not to include these things into the yield limit and the entire machinery of plasticity? Because nothing then will change. And in addition, despite the fact that I have proposed that in 2002, I confessed openly to everybody that this is a copy of Prager's thermoplasticity of 80 years ago, right? I have done nothing else but just replacing temperature with chemical variables. Okay, so here's an explanation. This mass of change of any substance is a result of the rate of chemical reaction. And this is a fundamental variable in geochemistry, or in chemistry in general, that essentially counts on the change of mass of the components that enter into chemical reactions. And we simply postulate that if you take away from a material a chunk of solid, this material becomes weaker, right? That's a gross simplification. There are many, many, many other things that chemistry can pull the trick on you that are not included in this formula. So there is a lot of things that you can argue that behave differently. Okay, what else? By the way, if you do a chemical reversal, so for instance, you have changed calcium ions into sodium ions, and then you change your mind and you change back to sodium, the reaction in terms of yield surface is exactly, again, like with temperature. It will not go back to the initial value, but it will account on the hardening that you have produced in between. Therefore, your yield surface after that period of the chemical reaction, if you return to the original situation, you have a much larger yield surface. Okay. Now we will concentrate a little bit on this mass of dissolved material. I should have changed that from quartz to calcite. I noticed that in this moment. So this is an example of very common thing of this dissolution of calcium carbonate. Calcium carbonate are the geological material that dissolves the fastest. Therefore, everybody loves them because you can do an experiment in the laboratory that will, in 2 weeks, show the results. If you do it on granite or in quartz, you have to wait half a year. So it's obviously that we love calcite. Right? So this is the reaction of dissolution of calcium carbonate in water that essentially produces the ions of calcium. And this is a carbonate ion, which is practically the product of it. Here, what you have is the taken from a reaction. I forgot. Well, Sjöberg is the guy that produced the equation for rate of reaction, which is the rate of mass of removal of calcite from any material. And this is his job. Here you have the molecular mass of the original material. Then you have the concentrations of various ions. And, well, this is the geochemical stuff. I am afraid even to speak loudly about that. I just religiously follow the formula and have it checked by a chemist after. Our addition is this. This variable is proportional to the specific surface area of the interface between solid and liquid, because what we have here, that from the solid, we dissolve minerals into the liquid, the pore liquid in this case. And this dissolution is, as in all the cases with dissolution, is proportional to the surface area of the contact. However, in materials that undergo plastic changes, this plastic change is, in some sense, is practically micro-cracking. And we have to introduce, well, micro-cracking produces a change of the interfacial surface area. Each crack, when it happens, opens surface area for dissolution. Right? So it immediately affects the product of the mineral or removal of the mineral from the solids. So what you have here is, surprisingly, that the chemical mass removal rate that you find in any textbook of chemistry is proportional to this mechanical variable. This is mechanical volumetric irreversible strain, for instance. You can put something else. And in fact, you can put here a deviatoric invariant, well, if you prefer, if you have data that confirms that. Anyway, so the first notice is that the chemical reaction rate depends on the mechanical side. So this is the counterpart to this, where you have the mechanical equations that depend on chemical variables. So we have a both-way coupling. Now, so I mentioned Prager, from whom I stole most of this stuff. So here he is in a picture taken in 1972 at Warsaw Conference of Plasticity. Right? So he visited us at that time. So imagine this is the classical equation of plasticity called consistency equation, in which we say that the yield limit changes in proportion. I don't know whether this can go away. Yes, in proportion to the stress increment and the increment in plastic strain or its measure. And we have added an increment of the mass removal. Right? So we say that the yield surface shrinks or expands depending whether we remove or add mass to it. It's a phenomenological proposal. You know, all plasticity is very phenomenological from that point of view. Anyway, so in case you say, I want to consider a situation when sigma is constant or sigma dot is 0, as shown here, what you get out, you get from this, equating that to 0, you get the response for plastic or irreversible strain rate, which depends or is proportional to the chemical rate at constant stress. So what we have here, we have introduced into time-independent plasticity, like this, a time dependence via kinetic rate equation. So this is what I promised you when I was campaigning for the chemoplasticity, that I will repeal and replace creep. And this is the replacement, right? The kinetic equation or strain rate equation is proportional to the chemical reaction rate. It's a proposal. It works in some cases. Here's an example that I worked a little bit with my Italian student, Matteo Centia. Southern Italy in Apulia has a very vulnerable coast. All these things fall down every 3 weeks a piece, right? So they are really worried about that. And, you know, they have restaurants here, so they are really worried about the process of progress of deterioration of the coast in its entirety. So the reason for that is the dissolution and suspension or resuspension and perhaps precipitation of calcarenite that does everything what it wants. And obviously, material goes. So here is an example of multi-scale approach to it. So what do? We take on a small scale a pore. We idealize it like this. P represents the overburden load, far away, right? We apply plasticity theory to it, and this is Zenon Mruz's and Kwaszynska idea, linearization of cam clay. This is the mean stress axis. This is a plane strain problem. So these are principal stresses. The pore is axially symmetric beautifully, right? And the only new thing is that the size of the Earth's surface depends on the mass removed, right? And the mass removed depends proportionally on the surface area, including the one that comes from volumetric plastic strain, right? Which represents here the increase of the walls of micro cracks. That's a little bit of phenomenological cooking, but as a variable, it should work. And so here it is, a portion of the material hardens and some softens. And as a result, the displacement of the inner radius of the pore is increasing, right? So the diameter is decreasing and the pore is closing as a function of time. Now, what you have here are different acidity of the material, right? So this is the most acidic pore water, and this is the least, okay? And these are results. For instance, this is the mass removal rate across the radius of the pore wall, right? With a jump in the middle between the elastic and plastic part. With jump in the middle because between the elastic and plastic portion. What is most interesting in this is this graph. This is the pressure, the overburden pressure, which is constant, as you see, right? This is the increase of the mass removal, and this is a responding displacement. I think this time it's at B, which must be the outer periphery of the pore, right? What is interesting is that the process goes from here, goes, and suddenly at point A prime, the solution that we obtained requires for the process to go ahead in terms of UB, requires that the chemical dissolution rate goes back. Since this never can happen in the situation which is there is a constant exposure to the chemistry, that generates a instability. So, for instance, from here to here is an unstable solution, which satisfies all conditions, but it is definitely, from our point of view, the choice between B and B prime and any other B's, etc. This is an instability caused by the chemical softening of your material. Okay. This is upscaling. I think I show you this figure, and that's it. And this is an experiment, a numerical experiment that my two Italian friends did on their own, in which they essentially allowed a chemical debonding of the material exposed to changing pore water, and that debonding started eating the bridge that is separate these two galleries, these two openings, right? So as you can see, the intensity of that increases, and finally, I think this is the failure situation. You can find the details in the paper, and I would like to conclude, but don't jump. It's not the end. There is a part 2. All right? So the conclusion is that modeling is a part of discovery. We discover more things that we thought we would when we started the modeling, because we are confronted with a number of questions and number of identifications of parameters of experiment that you have to invent when you go ahead. Scenarios are largely conjectures. You have to invent those horrible things that may happen to your structure, and they test them. And, you know, this is a conversation about what may happen. This is the essence of the performance assessment. You are supposed to prove that your structure will last for 200 years in all possible conditions, and it will not fail at the end at the extreme event. One thing that we do all the time, we, for instance, take single mineral to be dissolved, and chemists cry when they see that. They say, there's never one single mineral that reacts. All minerals are involved in the reaction. You have to write 200 equations of chemical equilibrium for all minerals, and that, you know, is a complex problem in numerical chemistry. And when you say, no, I'm interested only in calcite, say, it is civil engineers. Right. So anyway, we go ahead, and at least in this way, we are able to do something. Some of my colleagues did try to do more complete geochemical analysis, and they arrived at the reasonable results. Some of the mechanical phenomena can be explained via chemo-mechanics, and when I say that, this is the creep. I'm not saying that materials do not creep on their own. The creep, I mean, is the change in mechanical properties due exclusively to time as a variable, right? Or time of process as a variable. Here, what is better is that this time variable affects the chemical process, which affects the mechanical process, right? And you would have to fight all 40 million of chemists to say that chemical processes do not proceed as they say along the rate equations, right? So, well, this model that I presented is just very simple. Most of the constitutive functions are linear, so there's a room for improvement here. And what is also important, the multi-scale consideration. The progress is needed. There are methods that are embedded in finite elements to do this. They not always work, especially when you have multi-component process. So in the remaining 12 minutes, something like this, right? 5, okay. All right, I will talk about cracking. Desiccation cracking. Nobody likes cracking. And for instance, this is an unexpected product of an experiment that was done years back in Canada, not far from here, when they made the experiment with the heater embedded in the ground with the clay filling, and when they recovered everything after 900 days of heating, they found that the entire liner was completely cracked. And that was a shock. Here is another example of cracking that is not necessarily engineering, but is very evocative graphically. But I wanted to say something. You know, half of the soil mechanics today is the mechanics of unsaturated soils. And I want to bring my 3 cents into it. Desaturation, for me, is a 3-part drama. The first one, that is not very much discussed, is the cracking, macro cracking on materials that undergo desiccation or evaporation. Right? The second part of drama is the classical unsaturated soil mechanics has it that suction produces a huge artificial cohesion or apparent cohesion increase, which is true. You see, you know, these are macro cracks, and these blocks are hard as rock, right? So this is probably a clay in which this guy was planting his rice every year, right? So I'm not surprised that he complains. But these things are at high cohesion. But what you see, if finally the water would be also driven out from those blocks, you have a complete loss of local cohesion, and this whole ground will pulverize. Okay, since I have only 5 minutes, I will skip this. These are fundamental laws of evaporation, of transfer of liquid under pressure, which is Darcy law, and the fixed diffusion. And capillary laws that you should know because you have taken Physics 101 7 years ago. I will tell you 2 things about drying. So first of all, almost all material that are drying will crack. But they crack if they are constrained from shrinking, which is almost the case all the time. I did experiments like this, in which I would put a piece of wet clay or soil on Teflon, and I would let it dry. Never cracked, never. Now, if you put the same clay cake or soil cake on something that resembles the Great China Wall, that prevents it from sliding at the bottom, it will crack immediately. It's 7 points. It will crack first here, then here, then here, then here, always in the middle of the pieces that are left. Extremely repeatable process. All because of that material is constrained from sliding or shrinking at the bottom. So the first thing is, it's true that material cracks because the tensile stress induced by those constraints reach the value of the tensile strengths. Right? Tensile stress is induced by the shrinkage that is proportional to suction to close the pores as you remove water from the pores. Right? Okay. Okay, I will skip that. Suction is really the engine of the shrinkage. And interestingly, you will note that this is the water content. The material lose all water here, but the cracks happen when the material is half wet or still completely wet. In fact, they happen here. This is the saturation degree, meaning when the material starts being desaturated. So the cracks that you saw of this guy with the rice field, it has been cracked. But you see those cracks in material that's completely or almost completely dry. But the crack starts much, much earlier, which is a very puzzling thing. In fact, not recognized by many. All right. Also, what is interesting, that when cracks happen, which is more or less at this value of suction, right, and at this value of void ratio, so immediately after, the material stops shrinking. So there is a coincidence of those facts that let me think at the process of shrinking in terms of mechanics, because until now, all cracking stuff has been dealt by agricultural people, or most of them, or soil physicists. So what we also notice is that it is coincident with air entry phenomenon. Air entry phenomenon is when the material, when air starts to penetrate inside of the wet clay material or soil material. Anyway, so our review of this is purely mechanical. We say that soil is made out of pores that are cylindrical. These pores are in two main sizes, I think, yeah. These are large pores, these are small pores. They act separately and they behave separately. There are 12 small pores per one big pore. And they are well identifiable in terms of how many of them are and what is their average size. And the behavior is completely different. Okay, so now you can treat them with the elasticity driven by the evaporation process. This is the process of air entry, right? And everything starts immediately after. It's an extremely short process between this and stable pressure, so, which means no further deformation. Okay. Then you go to upscale it, and you recover the results, etc., etc. One interesting thing is a paradox, that if you consider everything what is happening there, you have an example that you have tensile cracks in compressed material, in material that is compressed through effective stress. And that can be resolved and has been resolved by a gentleman named George Schroeder here by suggesting that the flow from air entry into the material forms a stress concentrator, and that allows you to recover the tensile effective stress and the cracks. I will show you this one just to entertain you, if I may, or I may not. Well, I think Sonia have thrown a spell on it, and it doesn't want to show. Maybe I will be able to show this to you later. I lost it. Okay. What is interesting is this effect. So the last stage of failure, these are stages of drying. So this is the last stage when you have only the bridges between individual cracks, like this one. And this one will dry, but it will fail before it completely is dry. So this is another mechanical example of mechanical behavior of the liquid during drying. I will stop here with these two and will suggest the following. During last stages of drying of individual bridges, you have a very strange thing happening of the pressure inside of the bridge. What you notice is, for instance, that this pressure at this level at the beginning of drying is negative, meaning this is suction. At the end, it is positive, which means it's a pressure. So what you have here, you have a pump that simply pressurizes the bridge from here to here. It adds water. It sends water from here to here, and that leads to outflow of water in these directions, right, outside, and it provokes something that is called pinning of the bridges, and that leads to failure, and that's the end of the bridge, and that's the end of unsaturated soils, and that's the end of my talk.
Thank you. Unfortunately,
this is what you want.
The work of art, of original art.
So
by
this is your classroom.
Yes. Anyway, we have time just for 2 short maybe questions.
I'm curious about the focus of like degradation and performance analysis. Are we looking more for new structures and systems, or is there any way to sort of improve upon the materials of things that are already in place?
Well, I think it is meant to be for the future. We are sufficiently realistic to know that if you start reviewing all the structures, you will come with a very catastrophic view of everything, and there's nothing left than crying. But if you are to construct new concepts, like, for instance, nuclear waste or like CO2 sequestration, these designs should be treated with performance assessment.
Last question or comment?
Not question, comment. Supporting Copernicus is not a good reason to put Galileo to jail, but he should be in jail.
Right.
Because his answer to Holy Inquisition that displacement the cantilever beam is PL cubed divided by EI is wrong.
Is wrong.
It's divided by 3. EI.
Yes.
So, but the problem is what to do with the professors in 21st century who repeat the same error.
I have to check what is there.
Okay, comment on a comment.
It's not a comment. Okay, so
I'm listening.
the question that I have is the following: you treat everything within the framework of plasticity.
Right.
At the same time, the chemical reaction takes place at the surface.
Yes.
So I think you get away from that by invoking micro-cracking and maybe assuming that things are happening at the pore scale. But there's also a lot of things going on when you have localization. So structure fails via localized deformation. So I'm just wondering how you can, I mean, what is your answer to that? Because on one hand, plasticity is in the bulk.
Right. So the process of localization happens through a growth of micro cracks that the material tolerates to a certain degree. Now, imagine that the creation of those cracks is accelerated by the weakening of the material. So you have the process of localization will be accelerated. So I can imagine that I could, and I think there are guys around, in fact, the school of Yanis Vardoulakis that did that for Vaillant and for other instances for the faults generating earthquakes that did that type approach to the chemical processes affecting the strength of material. Yes, I agree. This is most of that stuff is in bulk, but you know you can certainly take an approach to multi-scale modeling in which you will have a map of or at least density of cracking and use that as a variable. So I'm not claiming that this is the final answer to anything. This is just the beginning.
Okay, it's the beginning and it's the end of the lecture. Please join me in thank you.
Sorry for